In the spring of 2016, a defense journalist sat down to write what he assumed would be a routine analysis piece about Russian ground equipment. He had covered armed conflicts, procurement scandals, and weapons programs across 3 continents. He thought he had a complete picture of what modern armies could do to each other. He was about to discover that the picture had a gap in it. When his article was published, something unusual happened. Editors at major defense publications in London, Washington, and Berlin flagged it for immediate republication. Within 2 days, the piece had been translated into 6 languages. A single paragraph from the article was being quoted in briefing rooms, circulated in email chains between analysts, and read aloud at staff conferences. Retired generals who had spent decades studying Soviet and Russian military doctrine were picking up phones and calling journalists back. The paragraph that caused all of this described a single Russian ground vehicle, not a ballistic missile, not a nuclear warhead, not a strategic bomber or a naval cruiser. A tracked combat vehicle, crewed by 3 men, that could reduce an area the size of 6 full football fields to scorched, airless, lifeless earth in under 10 seconds. And the most unsettling part was not the scale of the destruction. The most unsettling part was that there was no known way to shelter from it. The machine had a name. In Russian military documentation, it carried a formal alphanumeric designation. But among the soldiers who operated it and the officers who called for it in battle, it was known by a single word that, once you understood what this system actually did to its targets, felt less like a nickname and more like a confession. They called it Solntsepek. In English, the closest translation is something between scorching sun and blazing heat. And the reason that name fits so precisely is inseparable from the physics of how this weapon kills. But to understand why Russia built this weapon, why it works the way it does, and why, more than 4 decades after the first prototype rolled out of an engineering facility in Western Siberia, no other country in the world has managed to produce anything remotely comparable, you have to go back to the beginning. Back to a question that Soviet military planners were asking in the mid-1970s, a question that defense establishments in Washington and London were not yet taking seriously, a question that turned out to have an answer so effective that it is still shaping battlefield outcomes today. The question was deceptively simple. What do you do with an enemy who refuses to come out? By the middle of the 20th century, the science of killing people in open terrain had been developed into a precise and brutal discipline. Artillery, rocket systems, aerial bombing, all of it had been refined across decades of industrialized warfare into instruments capable of devastating accuracy against troops in the open, against vehicles on roads, against supply lines, command posts, and surface installations. Against these targets, the weapons of the post-war era performed exactly as designed. But there was a category of target that consistently frustrated military planners, and it was not a new problem. It was, in fact, as old as organized warfare itself. The fortified position, the underground shelter, the cave, the basement converted into a firing point, the tunnel network that allowed fighters to move beneath a city without appearing on the surface. Against these targets, conventional weapons struggled in ways that no amount of increased explosive power could fully solve. An artillery shell that detonates 20 meters from an infantry position in the open can kill every soldier in that position. That same shell, landing 20 meters from the entrance of a hardened underground shelter, may crack a few stones at the opening and accomplish nothing else. The people inside hear the explosion, wait for the sound to fade, and walk back to their weapons. The geometry of the problem is fundamental. Explosive force propagates outward from a point of detonation, and anything that places solid material between the detonation point and the people you are trying to kill absorbs a portion of that force. Put enough material in the way, and the force that arrives at the protected position is survivable. Aerial bombs operate on the same principle. Even large penetrating munitions, designed to drive through reinforced concrete before detonating, require a direct hit on the specific structure they are trying to destroy. A natural cave is not a specific point that can be targeted with a bomb. It is an irregular volume distributed through a mountain, and the entrance is a small opening on a rock face that an aircraft traveling at combat speed cannot reliably hit on the first pass, or the second, or the 10th. Soviet forces in Afghanistan learned this the hard way. Soviet military theorists in the 1970s were thinking about a specific future scenario: potential large-scale conventional warfare in the dense terrain of Central Europe, where an advancing force would encounter not just massed armor, but fortified urban positions, hardened command bunkers, and the kind of layered defensive infrastructure that a prepared defender had years to construct. They needed a weapon that did not simply project force outward from a point, but one that could flow into a target, follow its interior geometry, and kill everything inside, regardless of how well that interior was reinforced against conventional blast. The solution they developed was based on a physical principle that, once understood, explains everything about why this class of weapon is categorically different from everything that came before it. It is called thermobaric technology. The name contains the answer: thermo for heat, baric for pressure. Two separate killing mechanisms, one following the other in the fraction of a second between a warhead's arrival and the return of silence. Most explosive weapons work on a single principle. A rapid chemical reaction releases energy, generating a pressure wave that moves outward from the detonation point. That wave kills through force. It collapses structures, shatters bone, ruptures organs. The faster and more powerful the reaction, the larger and more destructive the wave. This is how conventional munitions have worked since the invention of gunpowder, and it is a principle that solid fortification genuinely does interrupt. Mass absorbs force, geometry redirects it. The engineering of protection against blast is mature, effective, and widely understood. Thermobaric weapons attack a completely different category of problem. When a thermobaric warhead reaches the calculated detonation altitude, typically a few meters above the surface, timed by an onboard fuse, it does not immediately release its energy as a blast wave. Instead, a small initiating charge fires. This charge does one thing: it disperses the warhead's main payload. Not an explosion in the conventional sense, a spray. A fine aerosol mist of combustible material expands outward from the point of dispersal in every direction simultaneously. This mist does not behave like a solid object. It does not respect walls, or corners, or sealed doorways, or the narrow entrance to a trench, or the gap beneath a reinforced door. It simply spreads, following the pressure gradients and air currents of the space it occupies, flowing into every available cavity, into the trench, under the vehicle, through the broken window on the ground floor of a building, down the stairwell and into the basement, along the connecting passage into the adjacent room. It occupies the same physical space as the people sheltering inside the fortification. Then the second charge fires. The ignition of a suspended aerosol cloud generates temperatures at the fireball's core that can approach 3,000 degrees Celsius. At those temperatures, structural steel begins to soften. Concrete surfaces crack and spall. The organic contents of an enclosed space, everything inside it that was alive, are not burned so much as they are simply converted into something else. But the fire, catastrophic as it is not actually the primary killing mechanism. The primary killing mechanism is what happens in the milliseconds after the fire. All of that combustion consumes oxygen, enormous quantities of it, drawn from every enclosed space within the blast radius. In an open field, replacement air rushes in from the surrounding atmosphere, and the effect, though dramatic, dissipates. But in an enclosed space, a trench, a bunker, a basement, a tunnel, the sudden removal of atmospheric oxygen creates a condition close to vacuum. And the atmosphere surrounding that space, still at normal pressure on the other side of the walls, and the reinforced door and the tons of earth and concrete above, rushes inward to fill the void. The resulting pressure wave travels inward rather than outward. It is, physically, the inverse of a conventional explosion. A wall of force moving toward the point of origin rather than away from it. This inward collapse wave is powerful enough to bring down reinforced masonry walls, to flip armored vehicles, to destroy structural elements that survived the initial fire. Anyone inside a sealed space who somehow lived through the aerosol ignition and the oxygen depletion faces a pressure wave amplified by the very geometry that was supposed to protect them. There is no practical countermeasure to this sequence of events in a conventional field fortification. A sandbag wall stops bullets and shrapnel. It does not prevent an aerosol cloud from dispersing through the surrounding air before it detonates. A reinforced door protects against external blast. It makes the inward pressure collapse more lethal, not less, because the sealed space has nowhere to vent. The physics are not negotiable. Soviet engineers understood this in the 1970s, and they built their weapon around it. The design question was not whether the warhead would work. The physics guaranteed it would work. The design question was how to deliver 30 of these warheads simultaneously to a target area from a platform capable of surviving the conditions of a frontline battlefield. The development contract went to engineering teams in Omsk and Tula, organizations with deep experience in armored vehicle design and in the chemistry of unconventional munitions, respectively. The challenge they faced was mechanical and immediately obvious. The launch platform needed to carry an array of large-caliber thermobaric rockets in a configuration that could survive the recoil of a full salvo. It needed protection sufficient to operate within the range of the weapons it would be engaging. It needed the cross-country mobility to keep pace with advancing tank formations. And it needed armor that could absorb hits from the kind of weapons an enemy would use against it, without triggering a catastrophic sympathetic detonation of the loaded thermobaric rockets above the crew compartment. That last requirement was the hardest. A fully loaded rocket array hit by a penetrating round would not simply damage the system. It would generate a thermobaric detonation that would destroy everything within several hundred meters, including any friendly forces operating nearby. The protection of the launch array was not a question of crew survival. It was a question of whether the weapon could be safely deployed in a contested environment at all. The solution borrowed the most proven armored chassis available. The hull of the T-72 main battle tank provided the foundation, stripped of its gun turret and repurposed as a carrier for the rocket array. The T-72 hull offered everything the engineers needed: exceptional ground clearance, substantial protection against the artillery fragments and automatic weapons fire likely to be encountered near frontline positions, the power plant to move a loaded system at speeds compatible with armored formation advances, and the mechanical reliability of a vehicle that had been produced in extraordinary numbers and operated under every conceivable condition. Above the hull, in place of the gun turret, rose the distinctive rectangular launch structure, an armored box containing 30 tubes, each loaded with a 220mm thermobaric rocket, all 30 aligned and ready. The resulting vehicle, designated TOS-1 and given the informal name Buratino after the Russian fairy tale wooden puppet, looked unlike anything in any other army's inventory. Western intelligence analysts who reviewed satellite images of Soviet test facilities in the early 1980s initially failed to identify the system correctly. The configuration, tank hull, no gun, rectangular superstructure, matched no known weapons category. It took years before Western assessments correctly understood what they were seeing. In 1988, with the Soviet military operation in Afghanistan approaching its conclusion, a small number of TOS-1 vehicles were transported to the country for operational evaluation under combat conditions. The scenarios selected for the evaluation matched the system's theoretical capabilities exactly. Fortified mountain positions, cave complexes, and defensive works in terrain that years of artillery fire and aerial bombardment had repeatedly failed to neutralize. What happened during that evaluation, according to the accounts of those who participated, was unambiguous. Positions that infantry units had been attempting to clear for days. Positions where concentrated artillery had accomplished nothing beyond disturbing the stones around the entrance were eliminated in single salvos. The thermobaric warheads reached inside the mountain in a way that no projectile and no bomb could replicate. The aerosol followed the passages. The ignition filled the interior. The pressure collapse brought the ceiling down. But the Afghan evaluation also produced a list of problems. The operational range of the first-generation system was approximately 2,700 meters for thermobaric rockets, close enough to put the vehicle inside the effective range of the shoulder-launched weapons that the fighters in Afghanistan carried in substantial quantities. And the armor protecting the launch array was rated to stop 7.62mm projectiles. Rifle fire, nothing heavier. A hit from any crew-served weapon, from any armored vehicle's main gun, or from any of the rocket-propelled grenades that were effectively the standard-issue weapon of the conflict, would have produced results too catastrophic to describe as merely a loss of equipment. The engineers went back to the drawing board with a precise list of requirements: longer range, much heavier protection on the rocket array, everything else preserved if possible. The solution they found required accepting a trade-off that looked on paper like a reduction in capability. The 30 launch tubes of the original system were reduced to 24. 6 fewer rockets per salvo, by any simple count a step backward, for a weapon whose entire value was the density of fire it delivered. It was not a step backward. The mass saved by removing 6 tubes and their loaded rockets was redirected entirely into armor for the remaining 24. The new launch array was rated to withstand direct hits from 30mm cannon rounds. The class of weapon carried by infantry fighting vehicles, armored personnel carriers, and dedicated anti-aircraft platforms. The gap between protection against rifle fire and protection against automatic cannon fire spans. In operational terms, almost every threat a vehicle is likely to encounter while operating in the same zone as tanks and infantry. The new rocket motors extended maximum range to approximately 6 kilometers, more than double the first-generation figure. 6 kilometers meant the vehicle could engage fortified positions while remaining outside the effective range of the light anti-armor weapons that had made Afghan operations dangerous. It meant the crew could observe the results of their fire, assess the damage, and decide whether to re-engage, rather than firing and immediately withdrawing under threat. The modernized system received the formal designation TOS-1A, and it received the name that would eventually appear in defense publications around the world, earn the grudging attention of NATO planners, and cause a particular quality of silence in certain briefing rooms. Soncopek, the scorching sun, the fire that doesn't need a target, the weapon that renders shelter irrelevant. A thermal imaging sighting system was added, allowing the crew to identify and engage targets in complete darkness, through heavy smoke, and through the dust and haze generated by the system's own preceding salvos. For a weapon that creates its own obscuring cloud with every engagement, the ability to see through that cloud was not a marginal improvement. It changed what the system could do operationally. The firing modes gave commanders options that the first generation never had: single launches for isolated targets, paired launches for rapid concentrated fire against a point, and the full salvo, all 24 rockets in automated sequence, away in under 10 seconds, for area saturation against a defended position or strongpoint. Within the ellipse covered by a full salvo, which measured roughly 40,000 square meters, the sequence of aerosol dispersal, ignition, oxygen consumption, and inward pressure collapse applied to every structure, every vehicle, and every person simultaneously. There is no account in any operational record of anyone surviving at the center of a full Soncopek salvo in an unprotected position. The first large-scale operational use of the modernized system came during the Chechen campaigns. The tactical environment was unlike Afghanistan in almost every respect. Not mountains and caves, but cities, dense Soviet-era construction, blocks of apartment buildings and factories that fighters had spent months converting into layered defensive fortresses. The standard approach to an urban defensive position, as described by officers who faced these structures, was methodical and effective. Ground floors blocked with rubble and sandbags, leaving only firing slits. Floors connected through breached walls for lateral movement without exposing personnel on stairs. Basements reinforced and interconnected by tunnels, functioning as command positions that could survive everything an attacker was likely to deliver from the surface. Against this type of position, conventional artillery worked on the upper floors and failed at the basement. Rounds that demolished everything above street level left the underground positions intact, and after an artillery preparation, the fighters in the basement walked back to their weapons and waited for the infantry to arrive. The infantry arrived, and the fight started again from the beginning. Soncopek addressed this differently. The thermobaric warhead required only proximity to an opening. A broken window, a collapsed wall section, the entrance to the building. Once the aerosol was inside, the sealed geometry of the basement and the connecting tunnels became an amplifier. The enclosed space concentrated the effect. The oxygen depletion was more complete. The pressure collapse was more severe. The structures that had been designed to survive conventional bombardment were, by their own geometry, ideal conditions for thermobaric weapons. Russian operational accounts from the Chechen campaigns describe a consistent pattern. When an assault on a fortified building stalled under fire from basement and lower floor positions, Sontsephek was called forward. The system took a position, acquired the target, and engaged. In the substantial majority of cases documented in operational reports, organized resistance from within the target ceased after the strike. The basement positions that had survived artillery preparation did not survive Sontsephek. The tactical doctrine that emerged from those campaigns has remained essentially unchanged since. The system never operates alone. It moves under the direct protection of tanks and infantry fighting vehicles, whose primary responsibility is not to support the thermobaric fires, but to prevent any enemy force from approaching the system while it works. The tanks face outward. The infantry holds the perimeter. Sontsephek engages the target. When the fire is complete, the entire force withdraws together. In every documented combat engagement conducted under this doctrine across more than 2 decades of operational use, through the Caucasus campaigns, through subsequent deployments, through extensive operations in Syria beginning in 2015, not a single TOS-1A vehicle was lost to enemy action. The record is, by any standard of comparison, extraordinary for a weapons system with that volume of combat employment. Syria presented conditions unlike anything in the system's operational history. The terrain was desert rather than mountain or urban, but the tactical challenge was familiar in its fundamentals. Fighters had occupied densely built city districts for years before the arrival of Russian forces, and the defensive works they had constructed in that time were mature and sophisticated. Buildings converted floor by floor into interlocking fire positions. Basements and sub-basements reinforced with salvaged concrete and steel. And beneath entire neighborhoods, tunnel networks of a scale and complexity that dwarfed anything encountered in the Caucasus. Passage systems that allowed fighters to move between city blocks without surfacing, to emerge for an attack and disappear before a response could be organized, to sustain operations in districts that were under constant surface pressure. Conventional bombardment against these tunnel systems produced limited results. A collapsing strike on one section of a tunnel forced a reroute. The network as a whole persisted. The aerosol physics that made Sontsephek effective in mountain caves applied with equal force to urban tunnel systems. The warhead did not need to penetrate deep into the network. It needed only proximity to an opening, a ventilation shaft, a section where the tunnel ceiling ran close to the surface. The aerosol followed the passages. The ignition followed the aerosol. Syrian army formations operating in sectors where Sontsephek had been employed reported a pattern that became consistent enough to be noticed. Positions that had been contested for months were cleared in hours. The combination of surface fires against above-ground positions and the penetrating effect of thermobaric warheads against tunnel networks removed the tactical advantage that the underground infrastructure had provided. After the fire, infantry entered positions and found them no longer defended in any organized sense. But Syria also confirmed the operational limitation that the engineers already knew about. Sontsephek cannot reload itself. After expending its 24 rockets, or whatever portion of them the mission required, the vehicle needed a dedicated support vehicle to replenish the launch array. That support vehicle carried replacement rockets and a crane system for installation. It had to be positioned near the Sontsephek during the reloading process, creating a period of vulnerability for both vehicles. In the relatively stable frontline conditions of the Caucasus campaigns, where positions shifted slowly and logistics could be organized methodically, this was manageable. In the more fluid environment of Syrian operations, where territorial control could change rapidly and maintaining a secure perimeter around a stationary 2-vehicle reloading operation was not always possible, the limitation had real operational weight. The engineers took note. When the third-generation system was revealed at a major military parade in Moscow, Western observers reacted with a mixture of surprise and careful reassessment. The surprise was immediate and visual. The new system rode on a wheeled platform, a heavy 3-axle military truck, rather than the tracked tank chassis that had carried every previous version. The configuration signaled something fundamental about the design philosophy. The T-72 derived chassis that carried Sontsephek was, by every measure, a proven foundation for a vehicle of this type. But it was a tank chassis, with all the operational burden that entailed. It consumed fuel at the rate of a tank. It required maintenance infrastructure appropriate to a tank. It wore through track components rapidly on paved surfaces. It could not cross bridges designed for civilian traffic without an engineering assessment. Moving it between operational areas required heavy transport vehicles. Moving it over long distances required rail. For a weapon that derived much of its value from the ability to concentrate firepower rapidly at a decisive point, these mobility constraints had always been a background limitation. The wheeled platform addressed all of them at once. A six-wheel drive heavy military truck travels at highway speeds on standard road surfaces for hundreds of kilometers without the maintenance concerns of track systems. It crosses bridges designed for commercial freight traffic. It drives to an operational area under its own power. Its fuel economy is that of a truck rather than a tank. The logistical footprint is smaller, the deployment is faster, and the range of terrain and infrastructure across which it can operate independently is substantially wider. But the most significant change was not the chassis, it was the auto-loading system built into the new vehicle. For the first time in the history of this weapon class, the system could replenish its own launch tubes without assistance from a separate vehicle. A mechanical loading system integrated into the platform drew replacement rockets from internal storage and reloaded the array without requiring an external crane or a dedicated support vehicle alongside. This collapsed what had been a two-vehicle operational unit into one. A battery of the new systems required no separate transport loaders, just the combat vehicles themselves. The reduction in logistical complexity was real, but the tactical implications were deeper. A self-sufficient system can operate in situations where bringing a support vehicle forward is not tactically feasible. It can fire, move to a covered position, reload independently, and re-engage without coordinating with a trailing vehicle. The tactical flexibility this provided was something that no previous version of the system had possessed. The number of launch tubes was reduced again, to 18 this time. This was not a reduction in capability. It was the engineering price of the auto-loading mechanism. The weight and volume it required had to be sourced from somewhere, and the designers took it from salvo size rather than from protection or electronics. The fire control systems on the new platform incorporated sensor fusion and targeting technology, more capable than any previous version, allowing engagement at greater ranges with higher accuracy. Fewer rockets, placed more precisely, accomplished the same objectives as more rockets applied less accurately. The designers understood this, and the trade-off reflects a mature confidence in what the weapon actually needs to do. What stands at the end of this story, after 4 decades of development, after combat operations across 3 distinct geographic and tactical environments, after the transition from a tracked prototype to a self-loading wheeled system, is a fact that should be considered carefully. Russia is the only country in the world that builds and fields this class of weapon. This is not for lack of awareness. The thermobaric principle is not secret. The physics have been studied, published, and understood by defense scientists in every major military power. Small thermobaric systems, aircraft-delivered bombs, shoulder-fired weapons, limited vehicle-mounted launchers exist in the arsenals of several countries. The United States has used thermobaric munitions in Afghanistan. Several NATO members maintain thermobaric weapons for specific applications. What no other country has built is the combination, a massed salvo of heavy thermobaric warheads delivered from an armored platform capable of operating in direct support of ground forces, protected and mobile enough to survive the conditions of a frontline engagement, with the institutional doctrine and logistics chain to employ it consistently across decades of real warfare. Part of the explanation is organizational. The Russian heavy thermobaric system lives within a specific branch of the military with a lineage in the Soviet forces that included unconventional weapons research going back to the Cold War's earliest years. The institutional knowledge, the operational doctrine, the training pipelines, the maintenance culture, the logistics, was built over decades inside an organization specifically chartered to maintain this capability. Building an equivalent from scratch requires not just engineering a weapon, but constructing the entire institutional infrastructure around it. Countries that have approached this from the engineering side, without that institutional foundation, have found the distance between understanding the concept and fielding a deployable system to be considerably larger than anticipated. Part of the explanation is political. Thermobaric weapons used in built-up areas have attracted consistent international criticism because the area effect physics that make them militarily effective also make them difficult to employ with the precision that discrimination between combatants and non-combatants would require. Several Western military establishments have been reluctant to invest in systems that their legal reviewers would find problematic to employ in the environments where they are most effective, which is precisely the environment of urban warfare that has characterized most of the actual fighting of the past 3 decades. And part of the explanation is simply that no one has found it necessary to match the capability, because the capability has not yet been used against them. The weapon that silenced a briefing room in Brussels in 2016 has been used in Afghanistan, in Chechnya, in Syria. It has not been used against a NATO formation. The incentive to develop a direct counter is abstract for military establishments that have not faced the weapon in the field. None of these explanations change the underlying reality. More than 40 years after the first prototype was tested, the gap has not closed. No equivalent system is deployed anywhere outside Russia. No equivalent system appears to be approaching operational readiness. The weapon that was designed to answer a question that nobody else was asking in the 1970s remains, in the most literal sense, in a category of one. There is something worth considering in the final accounting of what this weapon represents. The fortification, the act of placing solid material between a person and the thing trying to kill them, is not simply a military technology. It is one of the oldest human responses to violence. The cave that shelters, the wall that protects, the underground passage that allows movement without exposure. For as long as people have been trying to kill each other, other people have been finding ways to go underground and survive. Thermobaric weapons do not defeat this response by being more powerful than the protection. They defeat it by making the protection itself into the problem. The sealed space does not weaken the effect. It amplifies it. The reinforced wall does not reduce the pressure collapse. It directs it. The tunnel that was built to allow movement and survival becomes, in the presence of a dispersed aerosol cloud, a confined geometry that ensures complete oxygen depletion. The engineering of protection applied to any enclosed space works against the person inside when the threat is not a force that must be stopped, but a gas that must be contained. There is no known engineering solution to this. The physics do not permit one. You cannot build a wall that stops oxygen from burning. You cannot construct a pressure relief system fast enough to prevent the inward collapse. The only available response is to not be inside a sealed space when the weapon arrives. And the tactical reality of Sonsopek is that by the time a force on the ground knows with certainty that the system is in the engagement area, the rockets are already in the air. The defense journalist who wrote the article in 2016 was not being sensationalist when his paragraph caused silence in NATO headquarters. He was being accurate, and the silence was the appropriate response to accuracy, when the accurate thing being described is a weapon without a peer, without a counter, and without a timeline for replacement. The scorching sun, still in service, still burning, still without equal anywhere on Earth.